So we're going to talk a little bit about coastal dune modeling with airborne LiDAR, terrestrial LiDAR, and some structure for motion multi-view stereo, or SFM-MVS. I'm not sure if you can see the mouse pointer. So sand dunes are usually like a challenge for photogrammetry because they are quite homogeneous. They don't get good response in terms of spectral response, so you don't usually get good image matching. So we kind of took this as a challenge, and we wanted to do this comparison with some LiDAR data that we had from another grant project with these new drones that we just had acquired. Then we went for the field, we collected some LiDAR data, actually some drone data, and some terrestrial LiDAR data to compare the three data sets. So this is the study area. I go back to the methods in a second. We're in southern Brazil, just south of the very, very famous island of Florianópolis. And this is the Garopaba Dune field where we studied. We have the 2010 airborne LiDAR data that we collected in another grant. And this one is the DEM data from the drone data from the SFM-MVS method. And here you can see a small area selected. This is for the terrestrial LiDAR survey. Okay, so we used a LiDAR data from 2010 that was collected in a previous grant. It has a density point about 2 points per square meter. Okay, it's not much, but it's what we had, what we could buy at the moment. And then we went back in February 2019 for a field work where we took a faro focus terrestrial LiDAR with us, and we did 110 scan positions in that small area I just showed you. It took us 3 days to collect all that data, and then a lot more to align up the data into a single point cloud. We also took a DJI Phantom drone, and in about 3 hours, we did 6 flights and collected 810 images for the reconstruction. In terms of software, we rely a little bit on proprietary software, Ferrocene, Edgesoft, Metashape, LastTools, and mostly all the analysis we're running in open source software, mostly Grass, GIS, and Whitebox tools, all glued together with Python scripts in Jupyter notebooks. And all these notebooks are available. Okay, so these are the flight lines that we did, so 6 flight missions. The points here are the ground control points that we collected to georeference all the images. 6 control points collected with differential GPS. You can see one of the targets here in one of the drone images. And also you can see some of the sedimentary structure of the dunes here. And I say this because this will be important in a second. So going right into the results, this is the TLS, the terrestrial LiDAR, and the SFM DEMs. I mean, from the image, you really can't see much of a difference, except maybe if you pay close attention to this part here. Again, I'm not sure if you can see my mouse pointer. If you can see this in the bottom southeast-ish part, there's a little bit of roughness caused by a small, very low vegetation, but they're really, really similar, at least to the visual inspection. If we calculate surface roughness, and I am defining surface roughness here as the standard deviation of slope in a 5x5 window, we can see that in figure A, you have the TLS roughness. So it's really, really smooth. It's a really nice data set. It's really smooth. It only gets high roughness values in the vegetated areas, in the dune crests, and the dune break of slope in the foot of the dunes. Whereas the SFM DEM has a small scale roughness all around the DEM. You can see that it's not really as clear as the TLS. So it's a bit harder to try to derive dune crests automatically or something like that from that DEM. So I use the feature preserving DEM smoothing algorithm from our friend John Lindsay, and I try all kinds of window sizes and parameters. And then we get, here you can see in figure D, you can see the plot of all the parameters and how they change. And we end up with these parameters here, a K of 17 by 17 window, 20-degree threshold, and 5 iterations to get to this figure C, which is the SFM DEM filtered, the roughness of the SFM filtered DEM. So it gets really more a cleaner look, well, not much of that roughness scattered all around. It gets really better and it gets really nicer to see the results. So this is really good because it's a really good algorithm because you don't smooth your DM, you don't lose your features, you don't lose your breaks of slopes, and you still get to a nicer and smoother surface without losing much and without getting much of an error. Now, these are the differences between the terrestrial LiDAR and the SFM DEMs. The whole area is in gray. I cut it out a small area inside just to avoid any edge effect, any border effect. And you can see that it's kind of a bluish, reddish tone. So ideally, it would be white without any difference, but it has a bit of a difference. Not much. If you look at all the pixels, it goes from minus 1.5 meters to plus 5.5 meters. But those are just 300 pixels with a large difference into a larger universe. So actually, the difference are more into 30 to 50 centimeters. So the SFM DM is a bit higher in general than the TLS. I'm not sure exactly if that's because of the georeferencing or not. And that reddish bluish tone is because the point clouds, the individual scans are really hard to align. And we're talking about 110 individual scans. So it's quite hard to align that manually. And dunes are not the perfect environment for a terrestrial LiDAR. These LiDARs were made for engineering and architectural scans, so they rely on sharp features like corners of walls and pipes or whatever to align the point clouds. So we end up with a little bit of misalignment, but in the end, the point of this is that we consider that the SFM DM is a really good result. It really matches the TLS, which is a higher resolution, a higher accuracy data. So we get the idea that we can then use the SFM DM to compare with the larger ALS DLM, the airborne LiDAR DM. And there it is. So here in A, we have the ALS DM, the airborne LiDAR from 2010, the SFM DM from 2019. The color scheme is always the same. And here are the differences. We can see some major positive differences, which are obviously expected since the dunes are migrating. So we have accumulation of sand here in this really kind of central dune, as we call it. Some accumulation here. This is a vegetated ridge, so the sand is accumulating over the vegetation. And we have some accumulation here over the road. Also, if we could zoom in, we could see that the road here is pretty much in a gray color, meaning that there is absolutely no difference between the SFM DM and the airborne LiDAR DM over the road. So that is a stable feature. It means that we have a good match all around. If you look at histograms of the differences, you can see that there are a little bit of difference, but the histograms are really similar. And in terms of sand volume, there is no much of a difference. It's about 0.2% of decrease in 9 years. So that is something that we must consider. What's happening? Are the dunes not migrating? Is that not sand coming into the sand dune? What's really happening here? Because we would expect some difference. The point is that, of course, the dunes are migrating. We can see that from the images. We can see that from the DEMs. We have here the dune crests, and we calculated the dune migration. So it's about 5 meters per year, consistent with other studies in the same area. So why there is not much of a difference in terms of volume. Okay, so we can see here 2 profiles showing the dune migration. Here in these photos, we can see sand dunes, sand fences made to accumulate the dune over the fences. And here are the front part of the sand field here at that same road where I show you that picture. And the municipality of the region, the local government, has to remove the sand constantly from this area, otherwise the road would be blocked. So pretty much all the sand that comes into the sand field, into the dune field, is removed from its front part by the municipality. That's why we don't have much of a volume difference, even with almost 10-year difference. here jumping up to some conclusions really quickly. These two are quite interesting for us. First, that we did get a good image matching in all areas of the dunes, mostly because we could see the superficial features. So here's some superficial features like footprints, sandbar tracks, and the sedimentary stratification. And this is really nice because when we submitted the grant proposal, one of the reviewers said that this idea that we had was completely nonsense and that we shouldn't do it because dunes are homogeneous and we wouldn't be able to get a good image matching and we shouldn't spend any money doing that. But we were a bit stubborn and we did it anyway, and we got a good result. So, and one of the key findings is that, you know, we usually think of sand field trips, and we try to plan our field trips for good weather, to get, you know, really nice sunny weather and not going out in the field during the rain, of course. But sometimes with a little bit of overcast skies and some light rain, it can actually be helpful in this case. In this kind of environment, a light rain would be good because it will provide you will be able to see the stratification of the dunes. If it's really dry and really hot, you have that loose layer of sand over the dunes and you won't be able to see anything. So with a little bit of humidity, you can see things and you can get a really nice result. We validated the SFM DEM against the LiDAR, the terrestrial LiDAR, and we get good results, small errors, and the FPD denoise algorithm from John Lindsay is really a good idea to denoise these DEMs and still preserve all the features. Okay, we talked about the volumes, that they're really not changing much because the municipality, the local government, has to remove the sand. And just in terms of cost-benefit comparison, of course, LiDAR, airborne LiDAR is really good, it's really fantastic, we all love it, but it is of course expensive, and especially if you are in where I am in Brazil or in any other countries where we don't have government or statewide LiDAR survey programs, where we have to actually buy those surveys, so they're really expensive. The terrestrial LiDAR, by its turn, it has sort of an intermediate cost because you can rent the equipment and do it yourself, but then you will need a lot of time, you need more field work, you need more time. We took 3 days to collect all the 110 scan positions, so a lot more time, and with 2 or 3 students, those that are my co-authors, working pretty much full-time to align all the individual point clouds. It took them about 3 weeks to get all that done, so a lot of office work, a lot of time. Whereas the SFM MVS with drone borne images, it's really cheaper, really cheaper. With the money we pay for the TLS, we can buy another drone, and in about 3 hours we were able to collect all the data, and in another half day we were able to process everything in a medium range workstation, not even talking about a really good computer. And if you want to see a little bit more of it, all of this is published already, since we did it in 2019 and the conference was postponed. We already had that published in Computer Geosciences, the same paper. You can later massively will make the PDFs available, so you can just go right to the DOI, or there's also a preprint. So even if you're not able to access Elsevier's journals, Computer Geosciences, there's a preprint here, the very same content and everything. And all the data sets are available in Open Topography, all the LiDAR data, terrestrial LiDAR, drones, everything is in Open Topography. And all the Jupyter notebooks that we used are in the supplemental material and also in a GitHub repo. So you can access everything and do it yourself or just see how we did things. And I will end here. So thank you very much for your time. Also, really nice to be here again with you guys. And I believe we can have some questions. I usually don't use all my time anyway.